So I almost finished chapter 5 last time. There is a very small part. I want to finish it. So here, so last time in chapter 5, I explained how can you create a sequential circuit to detect 3 or more consecutive ones in a string of bits. Okay, so so as you see here, every time the circuit detects 3 or more, the output has to be 1, as you see here. The last 3 here are 1, so it's going to output 1, and so on. Okay, so I explained last time how can you create the state diagram, and I told you this is usually the most difficult part. How can you create the state diagram that can do exactly what you want to do? I can give you an analogy here. Similar if you have a programming problem, and then I'm going to create a flow chart. Okay, so once you have a flow chart, this is a difficult part. Once you have the flow chart, anyone who knows C can program it using C. If someone knows, for example, Python or Java, he can program it using Python or Java. So the next step is direct. It's very easy. It's exactly the same thing here. So the flow chart here, or the difficult part, how can you create this one to do exactly? Once you have this one, everything after that is very systematic. So I give you, I explained this one last time. I'm gonna explain another example, and which is very close to what you are gonna do in the second part of the project. So what you have to do exactly is once you do the state diagram, that's exactly doing what you want to do. You need to create the state table. Okay, and it's not difficult to create the state table. What you have to do here, you have to put the flip-flops you have. If you have input, you can put the input. As you see here, you need to put all possible cases here, all possible cases, and then you can get this the next state and the output. You can get them from the diagram here. You got what I'm saying? So for example, if it is 0 0 0, okay, so remember here I'm gonna S0 means 0 0. So if it is 0 0, for example, X is 0 and X is 0, so this diagram is telling me the next state has to be 0 0 and the output has to be 0, as you see here. You got what I'm saying? So all what you have to do to calculate the state table from the state diagram is you put all possible cases here, and then you can fill up this part from the diagram. You got what I'm saying? Okay, let me give you another example. For example, if you have here 1 1 1, okay, and then x is 0, let's locate it here. Okay, 1 1 here is actually S3, so here 1 1. So we are here and x is 0. So what should yeah, so that means this diagram is telling me if the current state is 1 1 and x is 0, so the next state has to be 0 0, and the output actually has to be 1, as you see here. So if you are in this state, the output is 1, right? But the next one is going to be 0 0. That's exactly what I did. So what I did here, I said, if I'm in this state, S is 0, so the next state has to be 0 0, and the current y is 1. So I took it from here. The current y is 1. Okay. Anyway, so then so again, this is just very systematic steps. Once you have this one, you have to create a table. Okay. Once you have a table, okay, next step, you have to decide which flip-flop you are going to use. Okay. So I can design this one using any type of the 3 flip-flops I explained. Okay. And then once I decide which flip-flop I can use, you need to calculate the input. What input in order to achieve this table? What should be the input of the flip-flops? So I give you here one example for using D flip-flop. Okay, so here this is the state diagram. So for if I'm using D flip-flop, so the input of the flip-flop should equal the next state. So this is actually, so if I want to get this next state here, this should be the input. Okay, I don't need to create a new column for the input of the flip-flop, because the input of the flip-flop should equal to this one. You get what I'm saying? So in next state, if I want to get 0, so I have to make sure in this input, the input of the flip-flop is 0. You got what I'm saying? So that is why this I don't need to create a new column for the input. If you want to do, that's okay, but it's just redundant. So what you can do here, I can say DA and DB and just repeat this part, put it here, and just take this part, put it here, because they are the same. Okay. So again, so now that's why I like D flip-flop, because it's just very easy, as you see here. So this should be the input of the flip-flop. And then after that, you can, now the problem became like combinational circuits. So you have here inputs, and then you have F1, you have F2. What circuit, what combinational circuit, given this input, is going to give you this output here? You got what I'm saying? So that's exactly what I did. So what I did after that here, given this input here, which, so here this is A. This is similar to what we did before. And then we have here, this is the second one, which is B. And then we have here, the middle here is actually the third one here, X. Don't be confused. Before we called it XYZ, right? It's the same thing, right? But just I use different symbol. I used here ABC, remember? Okay, it's the same thing, okay? So anyway, so once I do that, I'm gonna take here F1, and then I'm gonna do simplification using key maps, and this is the result I found. The result I found is, in order to get these values here at the input of the flip-flop for these input values, this is the equation here, okay? So it has to be DA has to equal AX or BX. That's it, okay? I'm gonna do the same thing here. I'm gonna do the same, because this is the input of the flip-flop number B, or flip-flop B. So it's the same thing. I'm gonna do simplification here and get another equation. For the output, so here also I'm gonna get the output here in function in these inputs here, okay? So I found this one. So now the conclusion is, yeah, that's what we have here, okay? And then after that, I am done. I can draw the circuit. So here, as you see here in the circuit, the input here, which is DA should equal AX. This is A, and this is X, so this is AX, or this is BX. This is X, and this is BX. That's it. So this is DA. Okay. I just draw it. Okay. Y should equal A and B. Yeah. So you can see here, I got this one from B. I got this one from A. So it's gonna be AB, and so on. Any questions? I explained this one last time. Today, I wanna show you how I can do the same thing, but using T flip-flop or JK flip-flop. That's what I'm gonna show you, okay? So let's move to the next one. What if I wanna use JK flip-flop, okay? Exactly same thing. Look here, guys. We have here, this is the input we have, okay? This is the input. This is the next state we have. All what I have to do, I need given this input, okay? I want to make the next state to be 0 and 0, okay? So the question is, what should be the input of the flip-flops, okay? Or what circuit I have to use so that given this input, I'm gonna get 0 and 0 after that. That's why you have to put here a new columns. These columns for the input of the flip-flop. So here we have two flip-flop, A and B. Look how it works. Very, very simple. I think I have a very nice diagram here. First of all, this is coming from the what's called the table. I forget the function table of the JK flip-flop. Okay. So this is coming from there. So if there is no change, you remember, so JK has to be 0, 0. If it is 1, 1, it means toggle. If it is actually 1 here and 0, that means it is reset. Where 0, 1, it means it is, sorry, this is reset, and this is set. Okay. So anyway, it's coming from there. So let's see. So now what I'm telling you here is, look here. If the input is 0, is that okay? No, sorry. If the current state is 0 and I want the next state to be 0. So what should be the input in this case? Or so the current state is 0 and next state is 0. So what should be the input of the flip-flop in this case? Okay. In this case, it can be two things, not one thing. Okay. So it can be actually, it can be so look here, J has to be 0, K has to be X. What it means? It means this one, it doesn't matter if it is 0 or 1. But how? I'm going to tell you how. Because if it is 0, it means no change. So if I have no change, so I have 0, I'm going to get 0, no change, or reset. So the two cases. That's why I'm saying here, if the current Q is 0 and then next Q should be 0, this can happen in one of two cases. Either 0, 0 where no change happens, or 0, 1 when reset happens. Makes sense? Okay. Let's look at the next one here. Okay. If I'm 0 and next time I want to get 1. Also, there are two cases. The first case here, it can be toggle. So 1, 1, 1, 1 toggle, right? Or it can be set, which set is actually here 1, 1, 1, 0. It makes reset. That's why I'm gonna say 1x. So if this one is 1, whatever you put here, either 0 or 1, I'm gonna move from 0 to 1. Okay. Same thing for the other one. So let's see here. I am 1 and I want to go to 0. Okay. Again, there are two cases, either reset or toggle. So toggle means 1, 1. Reset means 0, 1. Okay. That means X, X1. That's why you see here X1. Is that okay? So let's look at the next one here. If I am 1 and I want to stay at 1, again, there are two cases. Either no change, which is 0, 0, or this one can happen at set. Set means 1, 0. That's why you can see here, J is X. So it doesn't matter what you put here and then 0. Is that okay? So you should, so again, this table is just coming from the function table of the GK flip-flop, okay? I'm gonna use this table here in the design here. You will see how, okay? So look how I'm gonna do it. I have a very nice animation here, it's kind of animation. So here, let's look at the first one here. Now, as this one is empty, so I want to fill this one up. Okay. So look how I'm gonna fill it. Okay, look here. Now the current state here is 0, and next state has to be 0. So I'm gonna move from 0 to 0. So I'm gonna look at this table to move from 0 to 0. JK has to be 0x. So I'm gonna put 0x here. You got it? So here, in order, if you are 0 and you want to stay 0 next time, that means JA and KA has to be 0x. Okay. I'm gonna continue this way. Let's look at the next one. So 0 and then 0 again. So it has to be 0x. Okay. Let's look at the next one. 0 became 1. So I'm gonna go to the table. If I am 0 and next time I have to be 1, so it has to be 1x. Yeah, I think that's what I did in the next video here. Okay. So 0 and then 1, 1x. Okay. I have to continue this way. For example, if I go to, for example, the last one, if I am 1 and next time it is 0, so if you go to the table here, if you are 1 and go to 0, that means it has to be x1. So now I finished GK for flip-flop A. Then I'm gonna repeat the same thing again, but this time I'm gonna work on B. So here I'm gonna work on B and GA and GB and KB. Is that okay? So I'm gonna repeat it again. Okay. So very simple, because this is the current state, and I want next time to stay 0. What input, what value at JK to put it there? It has to be 0x. Okay. Again, then I'm done. Once you have this one, you are done. Okay, so I can, so once I have this one, all what you have to do is going to be similar to what we did in combinational circuits. So you have input here. This one becomes like function 1, function 2, function 3, function 4, and then using these values, you can get function 1. You can calculate it. This should be function in ABX. Same thing for 2. So in this case, you need to use. Here I'm explaining. You need to use simplification. Okay. Here that's what I'm explaining here. So here, if you are 0 and 0, that means I have to use this one here. So it has to be 0x. Okay. Same thing. If you are 0 and then it becomes 1, so I'm going to go to the table here. It has to be 1x. By this way, I can fill up this part, the input of the flip-flop. Is that okay? Yeah. So now, once you do that, that's what I told you. This one is going to be like function 1. Okay. This should be function in ABX. Okay. So I'm going to simplify by this way. As you see here, I can get GA. This is the input in order to achieve this column. In order to achieve from A here to get the A here, this is GA should equal to this value, and KA should equal to this value. Is that okay? Yeah, that's it. So now I have GA, I have KA, I have GB, I have KB. Someone can ask me, what about Y? Why you didn't? I don't need to calculate Y again, because Y will be the same. So when you change the flip-flop, Y will be the same. Okay, so I calculated Y here when it was D flip-flop. I already calculated Y. Okay, you don't need to calculate Y again when you go for any other flip-flops. Okay, just I need to change the input here. That's why if you want to calculate it again, you will get the same value again. Okay, so now, yeah, so now I'm gonna again explain how can you do it using T flip-flop, which is exactly the same thing. I'm gonna just repeat, right? So here in this case, as you know, in case of T flip-flop, okay, if T is equal 0, that means no change. If T is equal to 1, it means it's toggle. Is that okay? You toggle. So that means, look here, if the current value of the flip-flop is 0, and next time I want to make it 0, what's the input? I have to put it the input. Okay, I have only two choices, either 0 or 1. So now it should be no change, because no change happened. Okay, now if it is 0 and next time it becomes 1, so it's toggle. So T has to be 1 to get this new Q value next time. Okay, so given this Q value, okay, at this time, so T has to be 1. Same thing here. This one is 1 and becomes 0, so it has to be toggle 1 1, so it has to be no change. And then again, you already have this part. You got this part from the state diagram, but I don't have this part. I want to fill this part up. I want to fill this one up. It's very trivial. Look here, guys. Now 0, and then it has to stay 0, no change. Okay. Now it's very easy to use D flip-flop or T flip-flop. In my opinion, it's very easy because you have only one input. It's very easier than JK flip-flop. Now you are 0 and you are gonna stay 0. Okay, so it's gonna become 0. Now you are 0 and next time I want to become 1, toggle, so it has to be 1. Very easy, right? So if you look at the next ones here, 0 1 1 1, and then you have here the same thing, I guess. Yeah, here, look here, 0 1 1. It's the same thing. So here it's going to be 0 0 0. Okay. If you look at the last one here, toggle, because this one 1, and next time I want to get 0, so it has to, at the input has to be 1. Is that okay, guys? Same thing for B. Once you finish, once you have this one again, okay, so now it becomes like you have function 1, you have function 2, you have 3 inputs here. So you can use key maps to do the simplification. Once I do it, I'm going to get the input of register A and B. Any questions? Okay. The last thing I want to teach here in this chapter is, because you need something like that in the second part of the project in sequence detector. So I already give you one example to detect a sequence, which is actually, I want to detect if the sequence has at least three ones, at least. Now I want to give you another example so that this can help you in the project. I want to create a circuit that I want to create. Again, the most difficult part is creating the state diagram. Once you have the state diagram, everything after that is systematic. So that's why I'm going to stop here. I'm going to stop after finishing the state diagram. So now I want to show you if I want to detect this sequence 1 0 0 1. Okay, this is specific sequence. What should be the state diagram? Let's think about it. So I think it's better that I don't teach it from the slides. So let's do it here in a separate slide here. Let's think about it. Okay, so now the sequence is actually 1 1. Okay, 1001. This is the sequence I want to detect. Once you detect this sequence, the output has to be 1. Once, if you don't detect it, the output is 0. Okay, let's think about it. Okay, so now I'm going to assume we have states. Okay, so for example, I have here state S0. This is the initial state. Okay, so so if you are at S0, that means the last you have 0. Okay, you have 0. So if I'm in this state, and then after that I received 1. If I received 1, okay, which is the first one here in the sequence. So now I'm going to move to another state. I'm going to call it state 1. So if you are in state 1, that means you have only 1 here. In hand, you find only 1, which is the first one here. Is that okay? If you are here, okay. For sure, the output has to be 0 in this case. The output has to be 0. Okay. Okay. Let's start with the straightforward case. This is how you should think about it. The first straightforward case is, okay, assume you have the sequence. Okay. So after that, I got 0. So here, so initially I was here. After I got 1, after the input was 1, I moved from here to here. Assume I got 0. I got 0. So I'm going to move to S2. So once I come to, the only way to come S2 is if you have already 1 and 0. You have to go through 1 and then 0. You understand what I'm saying? So here, I'm originally here. I got 1, then I got 0. Is that okay? This is S2. Again, the output also here has to be 0. Okay. Let's think another. Then after that, assuming, so now I have 1, 0. Okay, assuming I got 0. Okay, so here I'm going to move to S3. So in S3, that means here when you have 0, I got if 0, so I got here 1, 0, 0. You can see here, if I start from here, I get 1 here, I get 0 here, I get another 0, I come to here. So the only way to be in this state is you have 1, 0, 0. Is that okay? Again, the output is 0. Okay, now that's my opinion. Try to start with the straightforward way, or not the straightforward, if you have the sequence. Because for every case, I have to decide 2 cases, if it is 0 or if it is 1. Here, I decided for 1. I'm going to tell you, after I finish, I'm going to go back and to try to, okay, but there is another case. What if it is 0? Same thing here. I decided for 0. I'm going to come back and see, okay, but if it is 0, I'm going to come to here. What about if it is 1? Because it can be 1 or 0. The input can be 1 or 0. Okay. So let's start with if you have the sequence. This is the easy way. Okay. Once I come to here, and then I got another 1. I got another 1. So what it means? It means I already detected the sequence. Okay. So now, I have to go back. I have to start over again to detect a new sequence. Okay. So in this case, I'm going to go back here to start over again. And then here, so I'm going to go here. If input is 1, and in this case, I'm going to make the output 1. Say it again. Initially, I'm here. Once I receive 1, I'm going to move to here. For sure, the output is 0 because I did not detect the sequence yet. Once you are here, okay, I got 0. So here, I'm just following the sequence. I'm here, I got 0, so I will be here. So the only way to come to here is by passing through S1. That means I should have 1, 1, 0. So if the input is 1 and then 0, I will come here. This is the only way I can come here. Okay. And then if I'm here and I got 0, so I will come to here. So the only way to come to here is if I get 1, 0, 0. Okay. Now, once I'm here and I get another 1, what happened? So I already got the sequence. It is the sequence. Okay. So in this case, I'm going to output 1. The output here is 1. Okay. If I get 1, the output is 1 to indicate I found the sequence. Okay. And then I have to go back here again from the beginning to look for another sequence, because it's not only one time, it's continuous. You got what I'm saying? Okay. Are you done? For sure, I'm not done. Okay. Why you are not done? Simply because I only consider one case here. It's a successful case if you have the sequence. What if you don't have? That's what I'm going to talk about. Okay. So if you are here initially at S0, so I have 0. Okay, I said if I detect 1, so I'm going to come to here, because this is What if I detect 0 instead of 1? So if I have 1, I'm going to come here. What? Let me use a different color because this is a color for successful case. Okay. Now, if here I have 0 and then I got 0, so what should I do? So I have to stay here, right? So if I get 0, I have to stay here because I didn't start yet, but because the sequence has to start by 1. You got what I'm saying? So as long as you have 0, I'm gonna stay here. So here 0, 0, 0, 0. I'm gonna move to here when I get 1 because this is the beginning of the sequence. Got what I'm saying? Now, if I have 1, I'm gonna come here. So this one is done because now I consider the 1 and I consider the 0. I consider both cases. Okay. Now, once I come to here, once I come to here, I told you, so I already have 1 here. I got 1. So now if I get 0, so now I'm going to move to here. What if I get 1 instead of 0? So now I have 1, and then I got another 1. What should I do? Should I go back to here? Yeah, should I go to 0? If you go to 0, that means you have 0 in hand. If I'm here, that means I have 1 in hand. So if I have 1, 1, that means I have only 1 from the sequence, which is the new one here, because it may be 1, 1, and then the sequence is going to complete after that. You got what I'm saying? So that means I have to stay here because I shouldn't go back to here. That means I have 1 in the hand. So now I had 1. Originally, I had 1 in the hand. Okay. 1 in the hand means it's 1 of the sequence. What I got 1 from the sequence. If I get another 1, so now I'm gonna stay here. So because maybe the sequence will start from here. I shouldn't go back to 0. If you go back to 0, the circuit may work in some cases, but it may not work in other cases. That's why I told you have to be very, very careful when you design this one. If you go to 0, that means the only sequence I can detect when it is 0, 1, 1, 0, 0, 0. But if you have 1, 1, 1, 1, 0, 0, 1, you are not going to detect this one. You understand what I'm saying? That's why I said you have to be very careful, because maybe your circuit is going to work in some cases, or the state diagram is going to work in some cases, may not work in other cases. So think about it. So okay, I go to just so here I have 1 in hand. Okay, I got another 1. So now I have 1 from the sequence. So I have to stay here waiting for, because maybe I'm going to have 1, 1, and then the sequence will continue. Okay? If I go to 0, so that means what is happening here is going to be different from what you want to do. That's why you have to be. It's similar when you write a flow chart. In the flow chart, I want to solve a problem in a certain way. Okay, and then you do flow chart that's going to do something slightly different from what you want to do. You got what I'm saying? Yes. Your question. This is a very good question. Wait a second, okay? This is, again, it depends on what it's like programming. So let me repeat the question because it's a very good question, okay? So the question now, when I come to state 3 here, okay, that means I already got 1, and then I got 0, I got 1. Is that okay? Is that okay? So the question is, why I don't go to here? Because I already have 1 in hand. That's the question. You got what I'm saying? For sure you can do that, okay? However, it depends on what do you want to do. Listen to me. So that's what we call this one. You want to make it overlapping between 2 sequences or not, okay? So it means, so here, if I detect 1, 0, 0, 1, okay, and then I have, so this is 1 sequence, okay? I need to take a new sequence like 1, 0, 0, 1 in order to indicate I detected a sequence. That's exactly what I'm doing here, okay? But if I take this one as a common, what's going to happen is that 1, 0, 0, 1, 0, 0, 1. So you're going to take this one as a sequence, and this one is a sequence. So this one can overlap 2 sequences. You got what I'm saying? So now you have 2 choices. So look here, it's exactly like a programming problem. Little change in the diagram here will make it somehow different, okay? So the way I did it here, once I detect the whole sequence, you have to go back here to get a new sequence. You got what I'm saying? So that new sequence has to be, so that means this would be the first case here. So once once I get 1, 0, 0, 1, okay? So I have to wait for another one to get a new sequence. That's what I did. This one is not going to be overlapped between two sequences. Sometimes some people like, it depends on what you want to do, okay? So if this one is overlapped, between the two sequences, so for example, 1, 0, 0, 1, okay, this is one sequence, and then this one I can take it again, 1, 0, 0, 1. So in this case, after S2, I have to move to here. Hopefully you got it, okay? So in a small change here, you will indicate, or the circuit will behave differently. It's like programming. When you do some change, it's gonna do something different, okay? So again, the reason I go back here, because I don't want this one to be overlapped between two different sequences, okay? So now let's continue here. So now I finish this one because I consider the 0 and the 1. I finish this one because I consider the 0 and the 1. Okay. Let's come to here of S3. So in S3, I already have 1 and 0. Okay. So if I get another 0, I already consider this case, which is here. But I didn't consider the case, what if I get 1? So it's already I have 1, 0. And then I got 1. What should I do? 1, 0, 1. What should I do? Where I have to go? What do you have in your hand from the sequence? What do you have? Only 1. Okay. So now, if you have 1, 0, this is the sequence I'm looking for. I got 1. I got 0. I'm very happy for that. But next time I got 1. You got what I'm saying? That means I'm gonna start looking from this one. Hopefully I can get 0, 0, 1 after that. That is why if I'm here and I get 1, if I get 1, I have to come to 1 and 0. So I have to go here, because that means I have 1 in hand. I have only 1. So I have to come to here. Is that okay? Let's look at the next one here. Yeah. Let's look at this one here. Now, so again, I am done. Listen to me. You are done. If for every state you consider 0 and 1. You consider 0 and 1. You consider the two cases, two possibilities. Now, if I come to here in S3, okay. So now I have 1, 0, 0. Is that okay? And then after that, I got 1. Okay, that's why I'm going to go again to look for a new sequence, and the output has to be 1. Is that okay? What if I'm looking for 1, 0, 0, 1? Okay, but I got 1, 0, 0. But after that, I got 0. What should I do? Where I have to go? So 1, 0, 0. So I was happy, I got 1. Yeah, I'm happy. 0. Hey, I'm happy, I got 0. 0. I'm happy, I got 0. I'm very close to do it, but I got 0. So what should I do? You break the sequence. So I have to start over again. I have to look for 1 again. You get what I'm saying? That is why I have to go back to here to start for a sequence again. But this time I'm going to say if you are 0 and the output is 0, not 1. So here I'm going to come to here to start for looking for 1 again. Any questions? Yes. This is not something you should guess. Okay, so either I have to tell you, or if I don't tell you, when I grade, to be fair to you, when I grade, I have to consider the 2 answers correct. So I have to be very, very clear. It's not something you should guess. You got what I'm saying? Any questions? Again, this is the most difficult part. It's similar to programming. The most difficult part is how to create the flowchart. Once you create the flowchart, anybody, if you know programming, you can just program it. Very easy. It's the same thing here. Okay. Anyway, so I think I'm done. I think, yes, I'm done with this chapter. So what I'm going to do now is, any questions here? Okay. So I left several parts in chapter 4. I want to finish them. Okay. So here, you remember in this chapter, I explained how can you design combinational circuits. Usually, combinational circuits are much easier to design than the sequential circuit. So I already explained how can you do adder, subtractor, BCD to X3 code converter, And now today I left this part. How can you do multiplier and magnitude comparator? Also I left this part. How can you do encoders? I hope we can finish them so that I finish chapter 4. So let's start with the first one here, multiplier. You can tell from the English name, I want to make a hardware circuit to do multiplication. So for example, I have a circuit here, and then I have a number here, B. I have another number here, A, okay? So this one is n bits, this one is n bits, and then the output here is gonna be the multiplication, A times B, the multiplication. You got what I'm saying? So you have hardware circuits similar to the other, but instead of doing addition, I wanna do multiplication, okay? So let's see how we can do multiplication in binary. I think I explained it before. Yeah, for example, as you see here in this example here, if I want to do multiplication, similar to the multiplication you are doing in decimal number, we're going to use exactly the same way, okay? I think I explained it before. So let's see how it works. What you have to do is that you have to take this number, you have to multiply by this one, and you have to multiply by this one, okay? 1 times 0 is 0. 1 times 1 is 1, okay? Then you have to take the second number here and also do the same thing. This is exactly similar to what we do in the decimal numbers. 1 times, and then you have to be shifted by 1. You have to shift by 1, okay? So now 1 times 0, 1 times 1 is 1. Is that okay? And then after that, you need to do addition. You need to do addition. This is how we can do multiplication. So if you see, this is number 2, right? And this is number 3, and this is number what? 6, okay? 2 times 3 is 6. Is that okay? Okay, let's see how can you do multiplication, how I can do hardware circuit. Listen to me, it's very easy. How we can do hardware circuits that can do multiplication. Is that okay? So in general, so this is a specific example now. It's the same example, I'm gonna do it in general. So I have 2 numbers. Every number is 2 bits. I have here number B and I have number A. So number B, it has B0, which is the first bit, B1, which is the second bit. Now number A has 2 bits, E0 and E1. Is that okay? You should understand what is the difference between A, when I say A, and E0 and E1. A means 2-bit number, E0, if everything here is bits. So this is the first bit, second bit, first bit, second bit. Is that okay? So how can we do multiplication? Look here. Again, similar to what I explained, you have to multiply this one and you have to multiply with this one. That's what I did here. And then you have to multiply this one by this one. You have to multiply this one by this one, okay? And then you have to shift. You have to shift by 1. That's exactly what I did here. After that, you need to add. So this one is gonna just come here straight. These two, I have to add them together. If there is a carry, has to come here and add these two together. And if there is a carry, the carry will be this one. Make sense? Okay, look at the interesting part. The interesting part, if you look what operation I did here, okay? If I'm gonna multiply 2 bit by 2 bit, what operation I did here? Number 1, what operation? What do you need? I need a way to multiply bits, bit by bit. This is number 1. So here I multiply bit by bit, bit by bit, bit by bit, bit by bit. This is number 1. So I need a way to multiply bit by a bit. This is number 1. Number 2, I need addition, because you need to add these two together, and then you need to add these two together. Other, I already explained half other. I already explained full other before. In case of half other, you have 2 bits. You are gonna have result or sum and carry. In case of full other, so actually you have 3 bits. Actually, one of them is the carry. One of them is the carry. Carry resulted from the previous one, or 3 bits, and then you have here sum and carry. So I already explained how can you do other before. So what else I need here to create this circuit? I need to know how I can multiply bits together. And you will find something very interesting here. Let's look what is interesting here. Very interesting thing. For example, look here, guys. Okay, now I want to see which gate I can use to multiply bit by bit. Okay, so here, look here. If I multiply 0 by 0, I have to get 0, right? Multiply 0 by 1, I have to get 0. Multiply by 1, I have to get 0. Multiply 1 by 1, get 1. Is that okay? This is how multiplication should be done, bit by bit. Okay. which gate I can use to do this one. Very, very interesting. And can do that. So and actually it's gonna do multiplication bit by bit, only bit by bit. Why? I'm gonna tell you why. 0, 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. So that means if I want to multiply any two bits together, I can use and gate. And the gate also can do multiplication bit by bit, only one bit by bit. So conclusion. If I want to implement this circuit, I'm going to use and to calculate this one. I'm going to use and here, and here, and here. And then I'm going to use addition. Okay, and that's exactly what I did here. So see what I did here. So here, A0, B0. So here, this is the first output here. So the first output here should be A0 and B0. And this is the first output I got here, okay? Okay, the second one here, I have to get A0 and B1. This is A0 and B1. I have to add it A1 and B0, okay? A1 and B0. And the result of the addition should be B1. Yeah, the result. So here I can use half other here because I'm adding bit to bit. I'm adding 2 bits. There is no carry coming from here. It's the first one here. So I'm adding bit to bit. So half other is enough. It's okay to use full other, but the third input has to be 0 all the time. You know what I'm saying? Because here actually I'm adding bit to bit. There is no carry coming. Here also for this one here, someone can say, okay, so I'm going to get A1, B1, and this will be the output. That's not true because there may be carry coming from here. Don't forget, because of this addition, there may be carry here. So that's why I'm going to use another half other here. So this half other, see, this half other has this one here, A1, B1 as an input. Also, it has a carry resulted from this operation, which coming from this one as here. Is that okay? And then the output will be 2, and the carry, if there is a carry from this operation, this carry will be B3. Very interesting. So the way I did it, guys, very interesting. So now, if I want to multiply 2 numbers, I was able to break it down into operation on bits. That's why, okay. That's why this idea can work if you want to multiply 1,000 bits by 1,000 bits. This is a very general idea. Here I just give you example for 2 bits by 2 bits, but it's a very general idea. It can be for more, okay? But for this is going to be more complicated, but I can use the same idea because I was able to break the problem into operation done on bits, either addition or multiplication. Any question here? Okay, I give you another example here. If I want to multiply 3 bits by 2 bits, you will see it's exactly the same thing. So if you see here, again, nothing is new. I want to just multiply this one by this one, multiply this one by multiply this one. So this is what I'm going to get here in the first record here, okay? Same thing here. I'm going to multiply this one by this one and this one by this one. This will be the second record here. I have to shift. So this is how we do it. And then once you have this one, and all of this operation can be calculated using and, okay? Once you get this one, this will be the first output. And that's exactly what I did here. I got the first output. Okay. To calculate these ones here, so I need to add. I need to calculate these 2, and then I add them together using half other. Okay. So that's what I did. I have a half other here, and then I calculated these 2 values here, which are these 2 values here. And then I got B1. Okay. Let's look at the next one. Next one here, don't forget, there may be carry coming from here. That is why here I need full other. So that's why I have full other here. This full other, the carry that results from this operation, there may be carry coming from here, either 0 or 1, whatever result from me will come to here. And then I'm going to add this one to this one. So here, this one is here, and this one is actually here. Okay. Now, for the last one here, again, there may be carry coming from here. Okay, so I need to add this carry to this one. And this half other should be enough. So there may be carry here, and this is B2E1. Then I'm going to get some, and if there is a carry at the end, this will be a part of the solution. Any questions? It's the same thing, but I just made it bigger. I think now also in your textbook, they made it also more bigger. So I'm going to go through it quickly. Yeah. So now I wanna, it's the same thing. I'm gonna repeat. So now I wanna multiply 4 bits by 3 bits, as you see here. Okay, look how it works. But now, because it's gonna be a little bit complicated because you have more addition here. Okay, as you will see. But it's the same idea. This idea is based on 2 things. That's why it is general idea. Number 1, I need to multiply bits, and this is done by AND gate. Number 2, I need to add bits, and this is done by half adder or full adder. That's it. You got what I'm saying? So now it's the same thing. I'm gonna multiply this one by this one, this one, this one, this one. So this makes this record here. I'm gonna repeat again with this one here, multiply them here, and shift. This will mean the second record here. Okay, and then I'm gonna multiply this one by all of them here, and then I shift, as you see here. Okay, and then look how I get the output. Okay, so in the first one here, once you do this one, I'm gonna get the output. So here I don't need any addition here, just AND gate to get the output here. Okay, but look at the next one here. Next one here. So here I'm gonna these 2 bits, I'm gonna add them together. There is no carry. So if you have even half adder should be enough. Okay, so here I'm gonna get B1 for these ones here. Remember, so I have these 2. I have to add. If you have something here, you have to add it, and then you have to get a result from here. Okay, because wait a second, there is something here. What's gonna happen here? Now I want to add 3 bits. I want to add 4 bits now. Why? This bit plus this bit plus this bit plus the carry. If there is a carry, I want to add 4 bits. Look again, I'm gonna make it easy. If you have 2 bits, I can use half adder for 2 bits. If you have 3 bits, I can use full adder. What if I want to add 4 bits? You get what I'm saying? So the way you can do it is, look here, I'm gonna use 2 4-bit adders. Okay, I'm gonna use this adder here, and then the result of this one will be the input for another adder and add to this one. You got what I'm saying? So now here I'm gonna use 4-bit adder to do this addition. It's gonna add this one plus this one, get output this one plus this one, and then if there is a carry, it will come to here. So it's gonna do the addition of these ones here. So I already explained how can you do for adder before using sequence of flip-flops. I'm assuming I already have the circuit. Okay, so I'm gonna here add 4-bit to 4-bit, and then the result of this one will be the input here that will be added to these 4 bits. You got what I'm saying? So what I'm saying, it's similar if you have, like, I want to add 3, 7 to 9, something like that. I want to add them together. So I'm gonna add these 2 together first. Once I get the result, I'm gonna add this one. That's exactly what I'm doing. So now, that's why if you see what I did here, this is the whole circuit. So now I have 4-bit adder, as you see here. Okay, the first 4 adder. So let's go through it slowly. So here, first of all, I have A0, B0, and this is gonna give me B0, and then I'm done. Yeah, I'm done with this one. Yeah, that's exactly what I did here. So you have here A0, B0. I got the output, so the first bit is done. Okay. Now let's look at after that. After that, I'm gonna add 4 bits here to these 4 bits. But wait a second, there is nothing here. I can put 0 here. So I can put 0 here. So now I'm gonna add this 4-bit to these 4 bits. Is that okay? And this is exactly what is done here. So what is done in this adder here? So if you look at these 4 inputs, another 4 inputs here. If you look at these 4 inputs, you will find the exactly similar to these 4 inputs, putting 0 here, and the 4 inputs here. So I'm gonna add these 4 inputs to these 4 inputs. Okay. And then look here. The first one here will be part of the output. But the other outputs here will be input to the second 4 adder to add them here. That's exactly what I did. So if you look what I did here, so here the first one here will be B2. I'm done with this one. However, the other 4 bits, including the carry here, this will be the input for the second one to add. So this is exactly what I'm explaining here. The output here should be added to this 4 here. Okay, that's why I need another one here to do. So I need one adder for this part, and then I need another adder that's gonna take the result of this one here. The result will be here, and then add them to this one. That's exactly what I did here. Any questions? Assuming you have this one. I already designed this one before, 4-bit adder. I designed it before. Okay. If you have this chip, you can just use it this way. Very easy. Just you need to multiply bits and add bits. That's it. Any questions? Okay, let's move to the next one, magnitude comparator. So this circuit should compare between two numbers. So here, very simple. I think I have, yeah. So look here. I want to design a logic circuit. This logic circuit has two numbers input, A and B. Okay. This number can be 1 bit, can be 1 bit, can be 2 bits, 3 bits, whatever. It's a number. You understand what I'm saying? So it can be 1 bit, or I can design it for 2 bits, I can design for 3 bits, 4 bits, whatever. So comparator is a logic circuit. You have two numbers, and then the output here should tell you, compare, you compare, should tell you if these two numbers are equal, if A is greater or B is greater. So actually the output here, only one of them should be 1 and other one should be 0. So if B is greater, so it should be this way. If A is greater, it should be this way. If they are equal, it should be this way. Is that okay? Any questions? Okay, I'm going to tell you, okay, how can we do it? Okay, I'm going to make it very simple. Let's look at, first of all, let's look at equal, okay? How I can know if two numbers are equal? You have two numbers. Let's look at, this is the thing we do in decimal numbers. For example, 370 and 370. How I can tell these two numbers are equal? How can you tell? Okay, all what you have to do, I have to compare digit by digit. If all digits are equal, so that means it's the two numbers are equal. You understand what I'm saying? So if this digit is equal to this digit equal, every digit is equal to the corresponding digit. If all of them are equal, so the two numbers are equal. You will see something interesting here, similar to what I did to the multiplier. I'm gonna break the problem down into bits, as you will see right now. So you will see. So it's the same thing. So if you have a number A, assuming this number is 4 bits, if you have number B, assuming this number is 4 bits, how I can know if these two numbers are equal or not? All what you have to do is that for this two number to equal, these two has to be equal, this two has to be equal, this two has to be equal, this two has to be equal. Is that okay? Assuming I have a circuit that can do that, so I'm gonna do AND. So the only way to get one here, is these two are equal, these two are equal, these two are equal to these two are equal. You got what I'm saying? That means the whole number is equal. Can anybody tell me what gate you studied in this course that can take 2 bits and give you 1 when they are equal? What? XOR? XNOR, thanks. Because, thanks, that's true. XOR is going to give you 1 when the two numbers are not equal. XNOR is going to give you 1 when the two numbers are equal. That's true. So all what I have to do is, I'm going to use XOR here. I'm going to use another XOR here. I'm going to use XOR here. I'm going to use XOR here. And then if this XOR giving me 1, and this one giving me 1, and this one giving me 1, and this one giving me this one, I can say the two numbers are equal. So that's why I can calculate this one. Is that okay? Good. So yeah, that's exactly what I'm saying here. So here I'm going to assume XI. XI is actually for every bit. I'm going to use XNOR. Okay. You know, XNOR is actually the complement of XOR. Okay. And this is XOR. Okay. This is XOR, and this is the complement. By the way, I'm gonna in the design, I'm gonna use this format. I'm gonna tell you why. It's the same, right? But I'm not gonna use this one, assuming I have XNOR. I'm not gonna use this one. I'm not gonna use this one, assuming I have an inverter and XOR. But I'm gonna use this one. Okay, I'm gonna tell you why. Okay, this will make the circuit smaller, but I'm gonna tell you why. But in exams, anything, if you want to use this, any one of these should be okay. So again, So I need to calculate the XNOR between every digit and the corresponding digit. If you give you 1, and of all of them give you 1, I can say it is equal. Any questions? Okay. So now I am done with equal. Now I'm gonna move to how I can know number is. For example, if I give you this number 372, okay, and 321, how I can know which number is? Let's start, for example, with 2 here. How I can compare these two numbers? How I can compare how I can know if this number is greater than this one number? How? Very simple. You have to start from the most significant digit here, from this here. You have to compare this digit with this digit. If this one is greater, so this number is greater. You don't need to continue. I don't need to check the other ones. This number 1. Okay. So I have to compare the most significant digit to the most significant digit. If this one is greater, I am done. This number is greater than this one. Is that okay? If this number equal 3 and 3, what should I do? I have to move to the next one. If this one is greater, so that is, I don't need to continue. This number is greater than this one. If they are equal, so I have to look at the next one. This is how we do it. Is that okay? So now I'm gonna do the same thing for binary. So if I want to know, I'm gonna compare these two numbers together. If A3 is greater than B3, so I don't need to continue. That means A is greater than B. Okay. If not, if these two are equal, so now I'm gonna look at this one. So now for A to be greater than B, we have several options. Number 1, the first possibility is that A3 is greater than B3. That's it. That's enough. Or now the relation is or, it's not and. Or A3 equal to B3 and A2 is greater than B2. Make sense? Or okay, A3 equal to B3 and A2 equal to B2 and A1 is greater than B1. And also these 3 are the last condition here. So I have 4 conditions. Any one of them, if it is achieved, so A is greater than B. That's why I'm going to use or this time. So I'm gonna, if this one is greater, okay, it's done. A is greater than B. If they are equal and this one is greater, this is the second condition. These 2 are equal, but this one is greater. The 3 are equal, but this one is greater. That's why we have 4 conditions. Okay. If any condition is satisfied, so it means A is greater than B. Okay. So now this is a very interesting part. Again, I was able to break the problem again to the bit level. Now I need to compare bits, similar to what I did in the multiplier and similar to what I did in the other. So I just add bits. Also, I need to compare bits now. So how I can know if this bit is greater than this bit? How I can know which circuit can tell me if A3 is bit greater than bit? How I can do it? So for example, look here, guys. Very interesting, very simple. If I have X, how I can know if X is greater than Y? Bit to bit. How I can do it? Any guess? What it means? Bit is greater than bit. What it means? It means this one is 1 and this one is 0. There is no other option. It's only one option. Bit X is greater than bit Y if this is 1 and this is 0. Do you have any other case? No, this is the only case, right? So how I can know if X is greater than, very simple. All what I'm gonna do AND. I'm gonna input here X, I'm gonna input Y prime. So that when X is 1, when Y is 0, Y prime becomes 1, I'm gonna get 1. Very simple, right? You got what I'm saying? So if I use here X, Y prime, so this one is gonna give me 1 if X is greater than Y. Make sense? Bit to bit, because I need to compare bits. Equal, I already explained how can we do equal using XNOR. Now I wanna get greater. Okay. So okay, what about it? So here if you put x and y prime, that means x is greater than y. I'm gonna get 1 when x is greater than y. Okay. Here, x is less than y. So here I'm gonna put here x prime and y. Is that okay? Less. So here x is less than y when x is 0 and y is 1. So in this case, it has to be x prime y. Make sense? So now I can, if I have 2 bits, I can check if the 2 bits are equal or not. I can check if 1 bit is greater than the other bit, or I can check if 1 bit less than the other bits. Okay. Now I'm okay. I have the quiz. If you want to take the quiz now, or maybe it's better. I wish you agree. Okay, I'm not gonna do it if you don't agree. Okay, if you can shift the quiz to next week so that I finish this topic, I will be happy. Sorry, not next week. Wednesday. Okay. If you want to do it now, I have the quiz. I'm totally fine. Okay. So next week, right? Sorry, Wednesday. I think all of you approved, right? I see you are smiling. You're happy. Okay. So let's do Wednesday. Is that okay? So that I can finish this topic. I don't want to break it and then come to. If you want to do it now, I'm totally fine. What do you think? Okay. Let's finish it. Let's finish this topic. Okay. So now, guys, now if you have 2 bits, I can easily, if I know, so if I use here XNOR x and y, so this one can tell me if they are equal bit to bit. Same thing if I use xy prime, so this one is going to give me 1 if x is greater than y. Listen to me. If I use here x prime y, this one can tell me if x is less than y. Is that okay? Bit, comparing bit to bit. Okay. So now, what I'm going to do right now is how I compare a number to number, because I already told you how I'm going to do it, right? So in order to compare a number to number, I need to compare bits to bits. And now I know how can I compare bits to bits. Okay. So let's start with the, I already explained the first one, which is actually, this one I already explained how can you get equal. So the A is going to equal to B if actually you need to do XOR, or I'm going to do it using this way. I'm going to tell you why. I'm going to do it using this way instead of this way. Okay. Why? I'm going to tell you why. Because actually you can see here, A prime B, A B prime. So these 2 logic, I already need them when I compare for greater or less. You got what I'm saying? So this will make the circuit smaller. So I can generate these 2, A prime B, A B prime. Okay. I told you A prime B means B is greater than 1. A B prime means A is greater than B. You got what I'm saying? So that's why I like this format. I'm going to use this format because I need to generate these 2 terms anyway for greater and less. Okay, so it may be easier to do this one. Okay. In exams, I didn't think yet how can I ask in this in this chapter, but typically if you want to ask in this chapter, I can ask you to design only circuit for equal. I can tell you have 2 bit. I want to compare 2-bit number to 2-bit. Okay, I make a circuit for equal. In this case, you can use whatever you want to use. Okay, as long as it's correct. Or I can tell you design a circuit only for greater. But here I'm designing a circuit that for equal, greater, and less. You get what I'm saying? Here I'm explaining it for 4 bits. But in exam I can only tell you only 2 bits, for example, or maybe 5 bits. For sure, I will not go 4 bits, but maybe smaller. But anyway, so now, so here, that's what I told you. In order to make sure A is less than B, okay, that means the last bit here has to be less than this one, and that's enough. Or the most significant bit is equal, and the next bit is less, or equal less. That's the idea I explained. Okay, you need to go from the most significant to the least significant. Same thing for greater. Same thing for greater. If A3 is greater than B3, that's enough. Or A3 equal to B3, and A2 is greater than B2, and so on. You got what I'm saying? So now you already have a circuit for equal. You already have a circuit for less. You have here less. You have greater. That's it. So now the problem became I can just create a circuit. All what I need here or here. For equal, I need NAND. Okay. So let's see how I made it. Maybe, yeah, maybe it looks too complicated. It is not. I'm gonna tell you how we made it. Very simple. It looks complicated, but it's not. Look here. The way I made it, if you look here for every part here, guys, if you look here you have A3 for this one here, A3 prime. Okay, so you can find here always one with inverter, the other input without inverter, and this one without inverter, and this one with inverter. Why? To generate two important things, which are A3, B3. One of them, for example, this one is prime, and A3, sorry, B3 prime. Okay, remember this one and this one. Why I need this one and this one? Because this one actually is going to become 1 if A3 is less than B3, and this one actually becomes 1 if, look, this is an interesting part. So that's exactly, I just want to make it simple because it looks complicated. It is not complicated. That's exactly what I did for every part here. So for every digit, as you see here, I generated these two magic terms. These two magic terms. This term can tell me this term is 1 if A3 is less than B3. This term is actually 1 if actually A3 is greater than B3. Is that okay? So 1 for 1. So you can see this way. So this input here is telling me if it is less. This input here, this one should become when it is greater. Is that okay? And now this is interesting part. If I take these two input and now I can make XOR out of these two terms, I'm gonna get equal. And that's why if I go back, that's why I told you I'm not, when I test for equal, I'm not gonna use this one, I'm not gonna use this one, I'm gonna use this term. Why? Because I need to generate these two anyway for greater and less. So once I generate these two terms, I can just use I can use NOR. I can use NOR to get equal. You got what I'm saying? So you can see here, if you look only at one circuit here, in this circuit, this one is 1 when A is less than B, bit to bit. This one is 1 when A is greater. And then I put here NOR so that using these two magic terms, if I NOR them, this one will be 1 if they are equal. You got what I'm saying? So now it became very simple. So for every 2 digit, I have three important things: 1 for less, 1 for greater, 1 for equal, and then I'm going to use them here. Okay. So let's see how. Look. So let's start with equal here. In order to say A3 is equal to B3, okay, that means all of them should be equal. That's why maybe the circuit is complicated, but you can see here, I'm gonna get this one here, I'm gonna get this one because this one is gonna be 1 if these two bits are equal. This one is 1 if these two circuit, and then I'm gonna get this one, and then I'm gonna do AND. That's exactly what I did here. Okay, because I have one bit here for equal. Okay, so if I take this one, input them to one AND, this will be, so here the output of this gate become 1 when this bit is 1, that which means these two bits are equal, these two bits are equal, these two bits are equal, these two bits are equal. Okay, so you can see here, guys, for every 2 bits I have three things: 1 for equal, 1 for greater, 1 for less. And then all what I have to do, very simple. Yeah, for example, if I wanna do this one for less, okay, I already have this one here. Then I'm all what I do, I'm gonna have OR. For equal, yes, I have equal. Okay, so that's exactly what happened here. So what happened if I take anyone else here, for example, A is less than B. The first condition here to happen, A0, it has to be, sorry, A3 has to be less than B3, right? So it should be enough. That's why this one is coming from here, coming from less. Okay, the other option is Here I need AND here, which is A3 is equal to B3, okay? And A2 is less than B2. And this is exactly what I did here. So equal, this one, remember, this is equal. So this is A3 equal to B3. I put here equal. And then this part here is less. And then I input this one to here. You got what I'm saying? And so on. So let's look at the next one here. In the next one, look here. I have to make sure 3 is equal. 3 is equal. Here. Sorry. So this is for the first one. For next one here, this one. For next one here. Okay. For next one here, I have to make sure number 3 is equal. That's why I have this one here, equal. Number 2 is equal. Number 2 is equal. And number 3 is less. That's why I get it from here. Okay, less. Okay. The other option, next one here, the last one I have here, look here, look this one. Number 3 is equal. Number 2 is equal. Number 1 is equal. And then I'm going to get the less for number 0. Okay. Anyway, it's maybe look complicated, but you can separate it. I'm totally fine if you separate it. But what I did here, guys, let me simplify what I did. Number 1, you need to know the operation I did for individual bits. Number 1, for equal, how I can know 2 bits are equal using XNOR. Number 2, how I can know if a bit greater than other bit or bit is less than other bit. And the way you do it, A prime B or B prime A. You get what I'm saying? Once you have these ones, okay, very simple. In order to, let's start with equal. So in order to have equal here, in order to say A is equal to B, that means A prime equal to B prime, and A1 equal to B1, and A2 equal to B2, and A3 equal to B3. That's it. So in exams, if you make it this way and tell me what should be here in every one, okay, I'm totally fine. Okay. Now that's exactly what I did in the figure here. Okay. Now let's come to less. Okay. When it is less, this is exactly what I have here in less. Number 1, this one. So now I have XOR this way. I have 4 cases. The first case is here. When this bit is less than this bit, which is actually A prime B, or these 2 equal. That's why in the circuit you have 1 for equal, 1 for greater, 1 for this, and then you can take whatever you want to take. So in this case, I need to do AND. I need AND here, and this AND, this 2 has to be equal, and this one has to be less. Or these 2 equal, and equal, and less. Or equal, and less. You got what I'm saying? So combine everything together, you need 1 OR, and that's what I did in the figure. Any questions? Okay. So we still have 2 minutes. So the last thing I want to explain here in these 2 minutes is actually last time, and also this is something you need to do in exams. You should not, I'm not asking you to memorize anything. If you understand how it works, you should be able to do it. For example, when I did decoder, you remember how I did decoder? Is the idea just for every input, I'm going to use only one end, and multiplexer is the brother of encoder, right? Of decoder. You just add 1 input. That's it. So very close. Okay. So now I explained decoder. I told you in case of a decoder, if you have 2 inputs here, okay. Sorry, if you have here 2 inputs, you should have 4 outputs. That's what I explained. You should have 4 outputs. Okay. So when the decimal value for the input is 0, so this will be corresponding to this output here. So the output 1, 2, and the 3. Okay. Always one of them is 1, and the others are 0. So if the input here is number 0, so number 0 is 1. Everything else is 0. If the input here is number 3 is 1, and everyone else is 0. This is how decoder is. Is that okay? What about encoder? You can tell from the English name. Decoder, encoder. Multiplexer, demultiplexer. It should be the opposite. Yes. So here, this is the input here. If I input 3, bin number 3 is 1, everyone else is 0. This is decoder. Encoder is going to be the opposite. So the input will be from here. Okay, so I'm gonna flip it, but this is the input and this is the output. You got what I'm saying? That's what we call encoder, just the opposite. So in case of encoder, if you have 4, 1, 2, 3, 4, I have here 4 inputs. For example, this is input 0, 1, 2, and 3. And then here I have 2 outputs here. If only one should be 1 and everyone else should be 0. So if number 3 is 1, so actually I should get number 3 from here. So here I'm converting. Only one here should be 1, and I'm going to get the number corresponding to which one here. If the 1 is here at 1, I'm going to get number 1 in binary here. If the number here is number 2, I'm going to get 2 in binary. It's going to be just the opposite. Okay. So next time I'm going to teach how we design it. It's just be very simple, so that I want to finish this chapter. Okay. Any questions? Okay. Thanks.